This question is about groups in the periodic table. The elements in group 1 become more reactive going down the group. Rubidium is below potassium in group 1. Rubidium and potassium are added to water. Predict one observation you would see that shows that rubidium is more reactive than potassium. Observations that we make during a chemical reaction are things that we would notice with our senses. And when you put the group 1 metals, the alkali metals, in water, they bubble, they possibly catch on fire, they move around, and they might get smaller and smaller and seem to disappear as they react. Now, if we are wanting to show that rubidium is more reactive than potassium, we must use comparative language when describing our observations. For instance, the bubbling might be more vigorous for rubidium, or the flame that we see might be bigger or brighter, or the rubidium might move around on the surface of the water more quickly, it might melt more quickly, or disappear more quickly. Any of these things, absolutely fine for the 1 mark, provided we use comparative language. And then in part B, we are asked to explain why rubidium is more reactive than potassium. Well, the group 1 metals all have got 1 electron in their outer shell, and they need to lose this electron in order to get a full outer shell and become stable. If we take a look at the electronic structure of the first 3 alkali metals, lithium, sodium and potassium, we can see the 1 outer shell electron in each of them, and when this outer shell electron is lost, the penultimate shell, that one that's just inside the outermost shell, becomes the new outer shell, and this is full. And so, if rubidium is more reactive than potassium, it must mean that the outer electron is lost more easily, or that it requires less energy to remove the outer electron. And this is because the atom is larger and has more shells. And so as a result of this, the outer shell electron is further from the nucleus, which is positively charged, and the electrons are negatively charged. And so this means that there is less attraction between that positive nucleus and the outer shell electron, which is negative. And we could also say, instead of that third point, that there is more shielding between the outer shell and the nucleus. And that means that the positive charge of the nucleus is being blocked or shielded by the shells between the outer electron and the nucleus. Complete the equation for the reaction of rubidium with water. You should balance the equation. And currently we've got Rb, which is a symbol for rubidium, reacting with water, H2O, and we are shown that it is turned into 2 things. We know there must be 2 things because there are 2 spaces with a plus between them. And we've got 3 marks, so the first mark will be for the first chemical, the second mark for the second chemical, and the third mark for the balancing. Well, first of all, let's look back at our observations. We see bubbling during this reaction, and bubbling is evidence that a gas is being produced. And in the case of the alkali metals reacting with water, the gas produced will give a squeaky pop when a lit splint is placed near it. And this is because the gas is hydrogen gas. Hydrogen is a diatomic gas, which means it has got the chemical formula H2. And the alkali metals are called the alkali metals because when you react them with water, they produce an alkaline solution. And that means that we're making a metal hydroxide. Any of the alkali metals, when you put it with water, will make a metal hydroxide. And so we're using rubidium here, so that means we need to produce rubidium hydroxide. And it's a group 1 metal, which means it has got a +1 charge as an ion, and the hydroxide ion has a 1- charge. So that means that the formula of rubidium hydroxide is RbOH. And then in terms of balancing, we currently have got one rubidium on both sides of the equation, so that is balanced. Hydrogen, we have 2 on the left and 3 on the right, and so that is unbalanced, and the oxygen is 1 and 1. And so we need the hydrogen atoms to be the same on both sides. That is what is stopping this from being balanced. And we have got 2 on the left, which is an even number, and the number that we put in front as a multiplier will always produce an even number. And so actually our big problem is making this even numbers on both sides of the equation. And so the way to do that is to turn the 1 hydrogen in RbOH into 2. And to do that, we need to put the multiplier 2 in front of RbOH, and this solves our hydrogen being odd on the right-hand side, because now we've got 2 times 1 is 2, plus the other 2 makes 4. And so to get us to have 4 hydrogen on the left-hand side as well, we need the multiplier of 2 in front of the H2O. So this has solved our hydrogen problem. And by having a 2 in front of the H2O and the RbOH, it has kept the oxygens as balanced as well, because we now have 2 of each of them. But the 2 in front of the RbOH means we now have 2 atoms of rubidium on the right-hand side, but only 1 on the left-hand side. And so to balance this, we need to put a 2 in front of the Rb on the left-hand side, and now this is a fully balanced equation, with 2, 2, and 2 getting us that third mark out of the 3. And incidentally, this equation is the same as it would be for any of the group 1 metals. All you would do is swap out the symbol Rb for rubidium and substitute in K for potassium, for instance, if it was potassium reacting with water. The noble gases are in group 0, which is a correct statement about the noble gases. The noble gases all have atoms with 8 electrons in the outer shell. This is not correct. Most of them do, but helium, the smallest of the noble gases, only has 2 electrons in its outer shell, and so that is false. The noble gases have boiling points that increase going down the group. This is in fact the true statement. The noble gases have weak forces between these single atoms, and these forces are stronger the larger the atoms are. And as you go down the group, the noble gas atoms get larger, which means their boiling points increase because these forces are larger and the atoms are harder to separate. The noble gases are not molecules with 2 atoms. They go around as single atoms, so that third one is false. And the noble gases react with metals to form ionic compounds is also false. The noble gases have no reason to react at all because they already have a stable electronic structure, because they have a full outer shell of electrons. The table below shows information about the 3 isotopes of neon. You can see that there are 3 isotopes of neon, each with 3 different mass numbers, 20, 21, and 22. And there are abundances of each of them given as a percentage. Mass number 20 has an abundance of 90.48, which means it is the most common, the most abundant of the 3 isotopes. Mass number 21 is 0.27%. Mass number 22 is 9.25%. And we've been asked to calculate the relative atomic mass, AR, of neon and give our answer to 3 significant figures. And there's 3 marks up for grabs here, which means the third mark of the 3 is going to be for the correct conversion into 3 significant figures. The relative atomic mass of any atom is the average mass of that atom, taking into account all of the different isotopes that exist for it. And so to calculate the relative atomic mass, you take the sum of all of the abundances multiplied by the mass number for however many isotopes there are for that atom, which is 3 in the case of neon. And then we need to divide that number by the sum of all the abundances, which, when we're working with percentages, is of course 100. And so the AR of neon is 90.48, that's the abundance of the first isotope multiplied by 20, and then add that to 0.27 multiplied by 21, and then add that to 9.25 multiplied by 22. And then we take that number and divide it by the sum of the abundance, which obviously as a percentage is 100. And so we get an answer of 20.1877. Since we've been asked to give this value to three significant figures, we need to remove the 877, but the 8 makes us have to round up the previous digit, and so that was a 1, it gets rounded up to 2, and so our final answer is 20.2 to three significant figures.